Good morning to all of you. I am Sandorkar. I am the oldest faculty member of the department. I am 29 years here. Uh, well, before we start, let me tell you this course. Analog is a course which will actually never leave you in your whole career, in case you remain engineer, irrespective of what engineering branch you take. So please pay attention to analog because, as the word suggests, it is continuous in time. And anything which is continuous in time must be important. Okay. Otherwise, world will collapse. Therefore, anything which is continuous is analog, and therefore it's very important. Before we start, there are a few things you should know. My name, as I said already, is Sandorkar. 6 credit course. What is this trying to do? Something that will try to see some of the analog circuits being implemented on bipolar as well as CMOS. It's very interesting to say that analog design appears to be much less systematic. Yeah, it is much less systematic. Whether some of those basic concepts which make it unsystematic are clear to you. Some of the books which I'll follow, the first one, you can see my name sitting there now, third author. Actually, I am not the author for this book, so it so happened that this Cedra Smith asked me to revise Asia and other countries other than US, it seems. So I added 150 pages to their earlier one, 1000 pages, and that's why I am the third author in that book. So since I am now part of the game, I'll use it as the textbook for me. However, if you have a book of Millman and Grabel, old book, by the way, this Millman person doesn't exist. Huh? This is like in my time, I think your father or their father maybe knowing the name called Thareja. Used to have electrical engineering by Thareja. Anything related to electrical, electronics, maybe civil also, he will write a book, B.L. Thareja. We are wondering how one person can have such a width. So it apparently found that Thareja's book became popular, so every other book from the same publishing house was written in the name of Thareja, so that it sells. Most well-known analog circuit person in the world. He is Dean of University, and of course his book is unsystematic to learn, but very interesting. Those who are really looking for very strong physics circuits, I think Gray's book is the best. And the fourth book, which I like normally, which is written by Niemann. Well, you maybe have read his other book on devices. The same author has written another book on electronic circuits and design. Okay, this is the syllabus which our site also gives. I don't have to talk too much about this. Something they are talking about operational amplifiers, frequency responsive amplifiers. This word which is Bode plot. Bode is a very famous feedback control system person, and in 1948 he wrote the first book on feedback control, and he actually described frequency responses. And for good reason, whenever I taught analog circuit, I also liked the frequency response part little more than others because connected to stability of the system. And therefore, of course, you don't say it, but 90s I was called Mr. Bode, probably because of my fancy for this Bode's plots. We will look into some applications of op-amps like comparators, clippers, and we will also see some oscillators, real operational amplifier, problems in amplifiers. Normally the old books have only bipolar transistors as their basic element, but since world has changed to MOS, we will switch more on the MOS, maybe 30 to 40% bipolar, 60% plus MOS, so that you know what's going on in the world now. So probably will, though it's not specifically written here, but I may actually switch more on MOS transistors, and I am told you have already been taught that, officially at least. Whether you understood, you liked it, you don't know, that's yours. But I am told you know it. Okay. And then in the end, we'll see some more applications like A to D converters, D to A converters, sample holds, and multiplexers, time permitting. Okay. So this is something about the course. Today what I am going to show you some slides which is just to tell you what's going on in the world. Okay. So something I will talk today about why analog, what are the analog issues, why CMOS. We'll just compare analog design with bipolar and CMOS and some systems. Please don't feel that this is irrelevant or something. Whatever I teach in the class throughout my semester, everything can be asked in the examinations, including today's talk. So I'll just give you some, what is VLSI, what are the technologies, what are the market needs, why analog designs are very important, and what are the challenges. Word VLSI has come from very large scale integrated circuits since 60s when the semiconductor chips have started coming in the market, particularly from Bell Labs and then from Texas Instruments. We started counting number of transistors per chip. So we say okay 100 small scale, 1000 maybe medium scale, 10,000 and above large scale, and maybe millions very large scale. So that's the number we are talking. This has happened because the dimensions of the transistor started shrinking from say 100 micron down to say nowadays 28 nanometers. So obviously if your dimension reduces, the number of transistors on the same area will increase. It's not so, the chip size itself has increased. Initially I had a chip which I made in 70s, was 1.5 mm by 1.5 mm. Today one can have 1.5 centimeter to 2 centimeters a side. So huge chips. For example, Intel, recent Xeon has around 940 million transistors. It has a 4 processor, quad processor on chip, and it has a memory of 16K SRAM, which is called cache, and just outside another chip they are kept in the same package, which is 4GB DRAM. You can imagine what kind of densities we are talking. But good thing about all this is only for digital. Analog people still talk about 1000 transistors, oh big circuit, huge circuit. Normally I prefer to have 10 transistors to 20 transistors, 50 transistors, huge analog block. The problem came because we have a technology earlier was bipolar transistors, and it is very ideal for analog performance. In fact, if you really want analog chip to work better, you actually go for bipolar. Two reasons we did not do that, or some companies still market. For example, some of the nationals OPAM 741 is still on bipolar. Okay, not all of them, but some of them. The reason why bipolar lost because of its density limitations, that because the size could not be reduced too much and used to consume huge power. And because of that, slowly bipolar gave way to MOS technology, and present day 99% or 95, 98% chips are on MOS. However, there is no system as far as nature is concerned which will not require analog. So a new concept appeared which is called mixed signal, analog plus digital. Analog may be 10% or 15% or even 5%, the rest will be digital. Now the issue came that if you have a digital technology, then I will prefer smaller dimensions because then it will be faster, I know. So I'll go for 22 nanometers, maybe 16 nanometer process. But analog says if it is a 1 micron, I am very happy. Larger it, better for me. Now that means you are trying to put an analog design on a digital technology which is worse for it. And now you expect that it should behave far superior. It's something asking too much. It's a paradox there. Analog designers left to themselves, they say, okay, put 1 micron lengths, channel lengths, it's great. Whereas digital will say put 10 nanometers if you can, 11 nanometers if you can. So there is a problem, and therefore the design and integrated circuit for analog plus digital has become very, very crucial because of bad technology circuit tricks, so that it actually does a lot of good things even with the digital around, and that's where the challenge is there. Therefore, there was issues whether we should work on bipolar or CMOS, and then in between someone said, why not work together by CMOS? Yeah, there are many good things about bipolar CMOS process. One of the thing, it takes some advantage of bipolar and some of MOS. But when I say some, there must be lot many disadvantages of both also must be coming. So you have to weigh whether this is important or that is important, and then go for BiCMOS. Only 6 companies in the world have BiCMOS technology, no one else. So what is the market is asking? Most of the market is saying wireless. Almost every one of you, I don't know, if one of you do not have a mobile, he should raise his hand. I don't think anyone will say, I don't have a mobile, because that's the only pastime you have these days, constantly putting here. So wireless systems have become so very important. This is the market need. So whole challenge nowadays is to work for wireless system. Major money is coming from wireless market. Then there is another system which is coming called optical system, particularly fiber communication, passing a good data from say hundreds and thousands of miles. Wireless doesn't work as good. So you want a cable. So a fiber was invented many years ago, and now we are looking for optical systems. The analog part came like this. If you have an optical system, obviously you are converting some data into through a photodiode into optics. You have LED and photodiodes, so you will convert one to the other, from optical light to the electrical and electrical to the light. And now these conversions have more problems. So the fiber will do faithful transmission, but what about the ends? So the major research right now, which has much of analog components there, rather optical analog components. Fresnel's laws, for example, are re-looked into now. The other area where analog circuits are very strong are sensors. You cannot survive without sensors, and we'll show some of them. For the digital side, you are looking for a microprocessors which is around, see your desktop, if it runs around 1 gigahertz and a DRAM up to 256 MB, and you are playing a video game. So you have to wait, वो आदमी मरता ही नहीं. Now what is happening, because neither there is enough memory nor there is a speed of the processor. So for this particularly game market, all over the world, including Sony PlayStation or Microsoft Play, whatever it is, there is a huge research in microprocessor speeds. So you can see bad things also lead to something good. And that is how we are looking for now around 6 gigahertz kind of processors. Normal Pentium 5, Pentium which you use, at least IIT has 2.1 to 3.2 gigahertz, and now we are looking for 6 gigahertz someday. Maybe ultimate aim is what we call as KU band 16 gigahertz, but we don't know whether we get there. I should not say we, I don't know, because I may not survive to see that. The another area of interest in market right now is memories. Just now I said, you want memories. 4 GB दिया तो बोले 16 नहीं है क्या, 16 दिया 256 नहीं है क्या, तो there is no end in requirement of memories, and and they want very fast access. So there are a lot of research going on in the area of memories, and the most important area, particularly I/O, input output blocks, which should be of low noise, low power, and very sensitive, and these are the active areas of research. The word custom means, in VLSI there are two kinds of designs we do. One is called semi-custom, the other is called custom. Custom essentially relate to customer. So customer says I want these specs, and you meet them. So obviously you have satisfied a customer, is paying for it now, good money. But that means every spec he says you have to meet, which is very difficult, because there is always what we call trade-offs. If you do this, something else will be lost. And to avoid that, we are trying to get the best out of it. So it takes huge effort, huge amount of design time, hundreds of man years to design a good custom chip. So what we do, okay, we pre-design some blocks and reuse it again, it's called semi-custom. So essentially analog designs, individual design has to be designed every time, and therefore it is called custom. And as I said, custom designs are costly, because it takes a hell of a lot of effort. Is that clear? The major challenge in either digital or analog is power and speed. Speed in our case of analog we call bandwidth. कितने gigahertz, कितने megahertz का bandwidth. Larger data can flow on the same line if you have larger bandwidths. So these are the challenges. Now question arises, why analog? Some digital system design, by the way, I have no fancy for digital or analog. I teach all sorts of courses. In last 29 years I taught. Last semester I was teaching a VLSI design course to postgraduate students. Before that I was teaching technology to postgraduate. Before that I was teaching digital system to second years. So I have no fancy for digital, but when I sit on this side I always abuse the other ones as if, oh, I am now this side. So this so-called digital designer suddenly said, oh, dead. 1980, he said dead. Last 10 years I find most of the research and most of the money has been now dedicated to analog. Partly because of the wireless, partly because of the sensor areas. Some answers, very simple. Nature doesn't like digital. You are not suddenly see, yes, there was no tree, today some full grown tree. It takes years, ages before tree grows. Nothing happens in nature which is instant. That is why when of course I worked in Tata Institute earlier, so I used to say Jayant Narlikar must be right because he is suggesting steady state evaluations. Because nature is normally prefers to go a steady way. But the big bosses are always saying Big Bang like a digit, 1 or 0. God knows. So what is important is nature being analog, even if you want to take that signal from the nature which is analog and you want to process faster, better, whatever you call digital people say, I'll need initial input outputs as analog. So I cannot avoid analog because nature is analog. What I'll do, okay, I'll take that analog signal, convert it into digital and maybe do all digital processing. At the end I want to display something, I'll convert from digital to analog and replace it back to analog. But I'll still require A to D and D to A converters. Most of the DSPs, digital signal processors, do this. Here is the problem. If I have an ADC, as I have an analog signal, the word analog essentially is time varying, constantly time varying signals are called analog. So this is analog signal, I'll convert it to digital table just to show you digital data and then I'll do digital processing. The problem with this, though it is shown as the same magnitudes, in real life the analog signal from sensor from nature is extremely weak. First amplified, okay, first amplified, then as soon as I amplify it will get some other frequency components. So I'll have to remove all those other than the signal I want. So I may need a filter and then maybe I'll further go to ADC and process digitally and at the end if I want output analog I'll convert it from DSP to D2A. So you can see that these two parts even in otherwise digital system will be required because otherwise I cannot process it. There is a lossy cable like a copper cable or any other cable. You send an input data and this is the data you are actually sending because it's not a lossless line. The actual data which is being sent is this. You can see it has a time period may be similar but its shape is does it look like analog? It does look like an analog signal. So you sent a digital data but data received in the output was more like an analog. Particularly this will be dominant if the frequency is very high. Okay, if you are looking at 4 gigahertz above or 1 gigahertz above, it's more likely that the digital data will be smeared to become analog. So even if I am fully digital person, now I'll have to worry about that the data which I am seeing being analog, how do I process it so that I still remain in digital domain. That is another problem which analog people are now coming to the help of digital. The way we do it, we convert it by some reason 4 levels of digital data. So a new technique. So far in digital, how many levels we were looking last semester or 10, upper level, lower level. Now there is a trend going on in a very high frequency domain to look for 4 level data. Okay. And if so, you will require 4 kinds of sensors now because it should detect 4 levels. Okay. Not that it has appeared in the market something. This is what I say going to happen now, that people may look for multi-level digital data to, because that analog part then can be broken into more levels instead of 2 only. Okay. So the newer research is now converting this so-called analog looking signal into a 4 level or even multi-level people are looking. Right now 4 is what is being attempted into a digital. So why analog? Probably I am trying to answer why analog. Okay. Most of the disk which you use hard disk, without hard disk you can't survive. 4 GB, 8 GB, 160 GB, 320 GB, kitna bhi do kam hai. This is your data you are storing on the disk, and what you really take it out is this if the GB speeds are higher these days, because you are making very high speed hard disk now, and data acquisition actually smears it, and the variation can be as high as 2 millivolt to some levels. Okay. Now again you will have to retrieve digital data out of this. This is called recovery. So another analog circuit will be required to recover from this digital data. So again there will be analog components. In wireless, you send the data at a particular frequency. For example, GSM sends the data at 890 megahertz. Yeah, this is your mobile communication signal. However, whenever you see something like passing a signal, there are two close by components which are called interferers. Okay. Now they are very close to the original frequency, and at times their amplitude may be larger. Okay. Because of the non-linearity in the system, you may get additional components which we'll call later some way harmonic, but these are not actual harmonics. Noise you may say, and they may have larger. So one of the major worry right now, either you boost this enough so that the interfered signal is much smaller than the signal itself, or shift this far away. Okay. Both techniques have been tried in the wireless communication, and both require a lot of analog processing. Just now I said optical, this is what optical receivers are. You have a transmitter, you have a laser diode, convert digital data or analog data into light, you pass through fiber. You have a photodiode which receives optical light, converts into electrical and processes. Much of the processing here will be analog in the case. Another area of interest, as I say, sensors. As I said, you want to measure temperature, you want to measure humidity, you want to measure all kinds of nature parameters. I'll show you some other kinds of them soon. The best sensors these days available are made out of another silicon technology which is called MEMS, micro electromechanical systems, okay, MEMS. And the most sensors which are now made available, which are very small, I don't know whether these days, in my time, we have a mechanical courses compulsory whether you do electronics or you do anything. So we have a applied mechanics course, we have a workshop, we have many other things also did, even the surveying, which I don't see anyone of, even civil people do these days. I'm not showing anyone theodolite and the chain and everything. Maybe it is there, I haven't seen it. So in the one of the famous gauge which mechanical people use called strain gauge. Okay. And that's a huge bulky dynamometer they call. Of course, they measure a lot of great large values of force as well as accelerations, but they are very bulky. Nowadays, sensors are very gyroscopes, for example, another big sensors, okay, vibration speeds. So now we are looking for silicon sensors, okay, and one of these method is to use capacitances as their measurements, because in the silicon I can make a cantilever which can under stress by acceleration or by force will vibrate or move down. The variation in this is proportional to the bending moment it got, which is proportional to the sense which it was doing. And the change here can be monitored as a capacitance. If I have two plates here, if it comes closer, capacitance is larger. If it goes away, capacitance. The change in capacitance is the measure of the force of the accelerometer. Okay. This is one more area which requires a lot of analog digital processing, which is MEMS. Another applications which are very important, as I see, is biomedical. Okay. I will not do all of them, but just to read for you. There is a many surgical operations. There is an issue because you will give an incision and lot of blood will ooze. Okay. And if blood is lost too much, patient will die because of loss of blood. Okay. Though they keep feeding blood. So there is some medicines they give Hyperion as they call, and it clots it. Okay. But if it gives too much, then they give clots in the veins itself. So blood flow will. So patient should not die is our major criteria. So we must keep monitoring the clotting level going on now. Okay. So this is essentially blood clot control, which in most of the heart surgery is very important because patient may die before you think. Therefore, in such applications, I show you analog processing is very important. Most of the college surgeries you can put right now, even there is a search going on for pancreas solutions, for heart patients. Everything is right now is replaceable. All kinds are put everywhere. Tantalum sheets are put here. So during this implant surgery, not much of control is required, which is continuous control, and you need a lot of analog processing. All your ECGs, EEGs, EMGs, ERGs, take and brains, any kinds of this body mapping, all requires analog processors. Then there is a biochemical spectrograms. It takes place, it doesn't suddenly happen. It keeps changing its pH values. Okay. So you want to know, you want to see what is changing. So a spectrogram is seen. So during patient is monitored when the drug is actually injected. So such, and this process is very slow. So you need a small signal which is appearing in electrical, has to be amplified, noiseless, because otherwise if there is a noise in that, you will get something wrong. You say pH is 7.5 and it may be 2 only. So there is an issue there, how to make a correct measurement of pHs. Another circuit which IIT Bombay has made, or rather product we made, of course I am not a party to that. Professor Sharma and my earlier colleague Professor Rakesh Lal, and even the Madam Shujai, I am told. These days there is a worry, even of course, I hope you are too young, and I only pray, touch wood, none of you will get your heart problems in your whole life. But it has been now found because of so-called money-making business of young students, young managers, they actually are getting heart problems at lower age than 40, which is unfortunate. Now, how do we know that the patient is actually having some problems? So we created a small kind of 2 probe meter, as say, which is small locket, which is put inside, bore like a. Then it monitors what changes from the last ECG has. If it is different than certain numbers, it actually has a RF transmit receive circuit. It will transmit to the patient is running on the track in the morning jogging, and he is feeling problem now. Hence, that it is happening to younger colleagues now. Okay. Another problem which analog people are facing is neurons. Your brain essentially works on the basis of neuron signals. Okay. And as I again said, all neuron processing is essentially like an analog. I'll show you some more time. A neural network which actually replicates a neuron behavior is like a op-amp characteristics. Okay. So you can actually think that a op-amp can replace your is equivalent. Say model. Okay. So that's very important that neuron theory stood on the hardboard using op-amps. Another area I just talked sensors. You know, anything you monitor inside the body is called lab inside your body, lab chip as they call. It will keep monitoring everything for you. Signals are weak, they have to block and sense. So you need a good eye for that. At the end of the day, whatever signal I get, I must reduce. It's a very small signal. I must amplify it. I must filter it. I'll see to it its replica of the original signal as good as possible. That's called signal conditioning. So these are the blocks. These are the areas where analog is used. Just I'll read quickly. Okay, I already said the person who does this machine is called perfusionist, whose role include monitoring appropriate parameters to ensure that the patient is effectively treated with anticoagulant to avoid blood clots. Okay. And for at least 60 minutes this is being monitored. So okay, this is more to tell you what kind of things happen. There is a thrombin and fibrogenin, two such parameters we keep monitoring, see what is the, but basically what electrical people monitor, it actually changes the impedance when it changes this. So all that we do is to monitor the blood impedance, and that monitoring will know whether what is the clotting level right now is going on. Okay, and then we can control it, that hyperon, how much to inject or not inject through this feedback system. Okay, so here is an impedance measurement system which is based on analog devices chip called 5933. You can see from here there are certain digital part, there are certain analog part. This is your oscillator, then there is of course multiplexer, then there is an interface, then there are digital block like registers, DFTs, but you can see there is a ADC, there is a filter, there is a gain amplifier. Okay, and you can see signals are analog and you are monitoring the impedance, the blood clot. How it is done is, this is how it is done. Your blood clots are kept here, then it reacts and then it keeps finding the impedance at the end. This is done in MEMS now. The chip is outside. This is the MEMS structure. Okay. And the whole processing is analog plus digital because something you have to control by digital. Okay. So you can see that only giving you one example why analog cannot be ruled out, that oh everything is digital, why analog? So yeah, there is a requirement where analog cannot be removed. Okay, I just said all that. Okay, another thing which people say, digital data transmission on a long distance leads to distraction, that is noise content. Hence, analog kind of transceivers will be needed. Now, question arises why we are not doing analog transceivers. This was known to us many years ago. 60s we knew analog better than digital. So why we not continued with analog? Why we? Major worry came that analog signal actually die down as they move to on the line because of loss it has. So you need a repeater. If you see optical fiber, every mile there is a repeater. So if you do same thing with analog, yeah, it can be done. But then again, you'll have to improve it by its low noise performance, filter it out. So cost involved. It's not that it cannot be done. It's just the cost involved and the power supply where you have to keep. So because of the cost involved in this, analog receivers have lost transistors lost to digital. Because digital signal can go far distance compared to analog and will require a repeater after maybe 20 miles or 50 miles or 100 miles. That is where short distance, why are we have a cable, why not use transistors which are far superior in performance. So at least locally we may come back now for its own fidelity or best performance sensitivity. We may come back to analog transceiver systems. Okay. For example, a normal hard disk there is a very little big signal, it's done, and the very high speed discs have come. So you need now something to amplify that. Similarly for wireless, the antenna, even for normal digital data, the antenna signal which you receive is dependent on from how far you are away from the tower. Okay. Of course, towers are not good for your health, that's what everyone is now saying. But I always say body is immune to everything after some time. So probably this so-called radiation will finally become immune to that, hopefully so. Okay. Maybe one generation. People asked me other day that you stay in Bombay, so much radiation from the DRC and Tarapur. I say I think our health is better now because of radiation, curing something, hopefully. Okay. That's the way we should look. Okay, I already said microprocessor memory with ultra high speed use clock signals across. The major worry, chip is 2 centimeter, I just said now. What is the length of interconnect on Intel chip? Anyone guess? What is the length of interconnect? Means a line taking signal from one point to the other. What is the length it actually transfers through on a chip? Typically, maximum lengths available on chip. How much? Any one of you guess? Nanometers. Typically, Intel processor has 1 kilometer length of interconnect on chip. Okay, and that's something you must understand. That we always think wire, big wire, but here on the chip itself, I have 1 kilometer. Now, if that is so, the signal will not have integrity going from one point to the other. That's our major. It's a lossless line. So the clock which is running from one end to the other actually drifts away. Okay. So let's say what is drift away means at t is equal to 0, let's say 1 has to come. At some point it will t 1 0 plus point something it will come because it get delayed by them. This is called jitter. And jitter is the major worry for digital data processing, forget about analog. Then the recovery of this can be done through what is called as phase lock loops, which is analog lock. Okay. That is why for clock recovery, you will require an analog circuit because you are running a very high speed signals on a large length of interconnects. Okay. This is like a transmission line. So all this memories have something what we call sense amplifier. What is sense amplifier can be? Let's say memory you have read, let's say you are storing 1 as 1 volt. Okay. If the line which is coming out where you call sense, I know the cell has 1, it takes long time because this wire is long enough, so it has a large capacitance, so it takes enough time before 1 volt it reaches. I don't want to know whether it is fully 1 or not. I have already pre-charged this line with say 0.8 or 0.6. Okay. As soon as this charging process crosses 0.6, I will compare. If it is larger than 0.6, I say 1. I will not wait for it to go for 1. This is called sense amplifier. Sense amplifier is a comparator which is an analog block. So even in the so-called hard memories, the major research, access time research is only on analog component and not so much on the cell. Is that clear to you? Why analog? Okay. In the case of digital, the circuit deals primarily with speed and power. I want a 4 gigahertz, 5 gigahertz data flow, and I want preferably 0 watt power consumption. Preferably, I want 0 watt. Of course, I know power cannot be 0, so as low as possible, microwatts, milliwatts, but certainly not watts. Typical chip consumes 40 to 100 watts of power. Okay. A microprocessor chip consumes around 40 to 100 watts of power. I want to reduce this. So the whole research right now we are looking is how to reduce the power, but there is a trade-off. As soon as I reduce the power, what do I reduce essentially? The current. If I reduce the current, power will go down, V into I. Okay. But if I reduce the current, the time taken for the capacitor to charge with the lower current will be larger, C dV by dt is smaller, so T takes longer. Okay, speed gaya. So there is a trade-off. So now game is, I want high speed, but I don't want to give you power. That's the reason. Thermodynamically, it should not be possible. If you don't give me this, I will not give the other. So how to fool thermodynamics is all our tricks. Okay. If you learn my digital course someday, I will tell you how I am fooling circuits. I am fooling others, beating as if thermodynamics is avoided. No, it cannot be. Somewhere else I am doing something tricks. As far as you are concerned, I have done it. Okay. I improved the speed, I reduced the power. Where did I spend? I am not telling. Okay. Somewhere I must have done. Some tricks I must have done. But as far as you are concerned, high speed, low power. That's where the research is about. In analog, these are not the two parameters we are worried. This is unfortunate. We worry about speed, power, gain, precision, power supply, variation in that, and many others, but at least 5-6 of them. You need large bandwidth, which is called speed. You need very precise, because why precise? Because analog is time varying signal. Any change there will be seen at the output. Okay. So precision means 1.6 millivolt means 1.6 millivolt. 1.7 किया तो उधर भी 10 times बाहर आ गया. So I am worried that what I say I must get that. Okay. So precision is very important in analog, not so much in digital. Why I say so? Because there is a noise margin. 1 can be recognized from VDD by 2 to VDD, and 0 can be recognized from 0 to VDD by 2. Anywhere is fine. Here anywhere means nowhere. Okay. And that is why analog needs extreme precision. Okay. Of course there also will beat the system. Don't worry, everywhere, like all IITians, brightest among them, they feel so. I don't know whether they are. Hopefully they are. You beat the IIT system. Okay. Not that you do good or bad. You see to it that whatever we come out with, how to beat it. Okay. 29 years, my experience. And we have lost. So I have full faith in you as well. Whatever way I will try to see you shouldn't do it, you will do it some way or the other. Okay. That's the IITian. So okay, worry, as I say, they are very sensitive to noise. What is crosstalk? Today, unfortunately for me, there is no crosstalk. Maybe this is your first lecture, you are worried about me. Good, keep worrying. Anything you talk there, if it interferes on me or my talk, it's called crosstalk. So two lines are going, one data on this, one data, this may interfere the next line close by because of coupling due to mutual coupling, particularly inductance, mutual inductance. Okay. This is called crosstalk. Particularly worse, if one data is going in this direction, the other is coming in this direction, the crosstalk is highest, both amplitude opposite. So maximum separation. Okay. So that's major worry in this interferers, crosstalks, sensitivity to noise. All these worries have to be satisfied when you design analog. That's why analog designs per se people say are difficult. Other worry of analog is even worse. Many times analog circuit books are called linear circuits. What do you understand by word linear? Why they were called linear circuits? Yes, linear. Okay, word in maths is y is equal to mx is a linear system. If I change x to 2x, y will also get doubled if m remaining constant. Okay, linear systems. Is that clear? Why therefore similarly analog circuits were earlier called linear circuits? Because output voltage was proportional to input voltage, gain remaining constant. V0 by Vn is constant, straight line. Okay. So it's called linear system. But our assumption is that the device property is always like this. That's why it translates input to output proportionally. But in real life, you have learned bipolar devices, you have learned MOS transistors. ऐसा ऐसा है, इधर भी ऐसा नहीं. So there is no real linearity in the MOS or bipolar characteristics. So there are regions where output current and input voltages, they are not linear, or input current to input, output current to input current not linearly connected. If they are not linearly related, then there is a second order non-linearity appeared. So to say y is equal to a0x plus a1x square, no linearity. Now this x square term will create, let's say sin omega t was the signal, x square will create what terms? Sin square omega t, which in terms of 1 minus 2 sin square omega t is sin 2 omega t. That means you have omega t terms and 2 omega terms also appearing. Is that correct? Harmonic has appeared. Okay. So part of the power has lost to second harmonic. Is that clear? So in the case of analog, you have a very small range which is linear. As soon as you increase the amplitude even a little more, you are in a non-linear range, and part of the power is anyway lost to the second or third or higher harmonics. Okay. So you have to be always worried you should remain within so-called that linear range. Okay. Otherwise, you will immediately get into second order device problems. Okay. These are very important effects. We will see how to minimize them, but not every time we can reduce to a zero level. Because of this so-called smaller range, so many effects it wants to do, it is very difficult for do automation like digital. In digital there are all kinds of software available, so much so nowadays there is something called silicon compilers. I give a statement, I want to do this under this condition, it should show me this, and a chip can be designed without your intervention. Okay. All simulators can do that. Okay. It will actually find out what you want, okay, and it will finally give a design for the chip. This is full automation. Of course, not the ideal. We still interfere everywhere so that we remain in charge. If everything is done by a computer, what will do? So we keep saying no, human intervention is essential. Okay. But otherwise, there is a possibility that automation is great in digital hardware, okay, or digital simulations. There is nothing so-called fully automated analog designs or analog systems. You ought to design every time because it's very problematic. Every small problem has to be individually handled and fixed. That's why analog is interesting, maybe difficult. And much of this, what is the way people do it? Not essentially always by reasoning, mostly by intuition and experience. Last time ऐसा हो गया, इस बार भी कर देते फिर देखेंगे, तो थोड़ा सा तुक्का भी चल सकता है. Economic forces require development of analog circuit in mainstream rigid process. That's what I said, and that is creating major problem because technology of digital, particularly at 45 nanometer down, is worse for analog designs. But we have to work with them. So we have to integrate analog digital on a digital process rather than on an analog process, which would have been ideal because if I want op-amp only, why should I put everything else? I want only this. I'll give very good to you. But I cannot because they'll say no, this has to sit with microprocessor, this has something else, put your block here, then what? There is the issue. So there is a difficulties in analog designs, therefore it's a challenge. So what is my answer to you? Is analog design therefore more difficult than digital design? My experience of 29 years says yes. Because digital design has a large noise margin, okay, you can have three-way trade-offs only, power, speed and maybe area. Whereas analog needs multi-dimensional trade-offs, power, frequency, gain, precision, power supply and many more. Okay, we are already done. Sorry. There are two possible technologies which analog circuits can be implemented using bipolar current transport, the bipolar transistors, or field effect based current transport, which is MOS transistors. Bipolar circuits have edge over MOS circuits as far as performance is concerned or gain is concerned, but has a drawback of large power dissipations. Whereas MOS technology for analog, though not the best possible compared to bipolar, but much more suitable for digital applications. CMOS is the best bet for digital and hence analog too should get implemented on CMOS. Not that it is better, but that's the necessity. as I just now said, mostly the chips will be mixed signal, both analog and digital together, like a neural say, and I'll show you some figures. Okay. This is a mixed signal neural processor. Okay. This is your digital signal, neural digital signal processing. This is D2A converter. This is analog neural network neural processing. This is A to D convert and feedback. This is a processor was designed way back in 1994 or something, which still works. Okay. We are trying to replicate brain functions now. We are trying to see how brain works. So tomorrow, if you have an accident or some reasons you have a damage to your brain, can I put a chip to supplement that part? This is what we are looking for. Is that clear to you? Why this research? Because there is a worry, there is a too much traumatic situation these days because the cars are too many, speeds are too many. Two-wheelers, if you are driving, please take care of old persons like me. Crossing a road at the main gate, I always pray God every second because I don't know whether I'll cross finally. When this motorbike person will not throw me. Okay. He doesn't see signals, he doesn't see people, I don't know, he only sees speed. Okay. So I hope some of you who have bikes, we have banned, I am told, but I still see hundreds of them. So in case you are driving, please take care of old people like us who still may want to survive at least few more years. So this is something what we are right now looking for. Okay, this is quickly I'll show you introduction to analog circuit. You can see here, this is a non-linear system and this is a linear system. Can you tell me why? Vin is ground or VDD is 1, V out is either 1 or 0. The reason is, since both are transistors and both are non-linear components. Okay. So V0, Vin, when you go from Vin from 0 to 1, both transistor will not remain in the same operating mode. That means one may be in linear, other may be in saturation. Other may be linear, the other, both may be saturation, both may be linear. Since the characteristics in all two zones are different, there will be a lot of non-linearity in V0, Vin characteristics called the transfers. We already done transfer characteristics. So that's a non-linear device. But in the case of analog circuit, we only operate this is the transfer characteristics of an inverter, which you just now see, CMOS inverter. You can see from here to here, V0, Vin is non-linear because here one is in speed in saturation, non-saturation, other is in saturation, both saturation, other opposite happens here. In the case of digital, signal goes from 0 to say VDD, input goes from 0 to VDD. Analog actually works only in this zone where relatively V0, Vin is linear. So you can see the available input range to me is how much? Few millivolts. Do you get the point? Because during this few millivolts only V0, Vin has relatively linearity, nowhere else. Okay. So what does that mean? The input signal in analog has to be small signal because otherwise it will not remain in linear zones. Okay. And that is why if you operate bias your circuit only in this range, let's say this is my biasing voltage, then I can apply an input signal over it which still keeps output such that V0 Vin is in linear mode. Okay. That is where the analog differs from digital. Digital I go from here to here. Analog I remain only here. Okay. And therefore you can see linear circuits will have always limitation of small signals. It cannot have, because you can see if I have these large signals, you are in non-linear areas. Is that clear to you? Therefore analog circuits normally will have very small signals limitations, because of course you can go out, then what will happen? The power will go into other harmonics more than maybe fundamental with the frequency you are 2 omega t, 3 omega t, 4 omega, 5 omega. More than nonlinearity, x square, x cube, x4, more third, fourth, fifth harmonics will start appearing. Plus another may appear, omega 1 minus omega 2, omega 1 plus omega 2 will also start appearing, which may be burst interferers. And therefore, analog people should normally try to operate themselves in the linear mode, and therefore signals are always limited. Is that point clear to you? That is why I say this is, so you can see if you operate in this, then you can remain as an amplifier, and then you can say you are in linear circuits. Just to compare again, digitals are highly nonlinear, but very high noise immunity. I just said VDD by 2 VDD 1, 0 to VDD by 2 is 0, huge noise immunity, immune to power supply variation. If 1 volt supply become 800 millivolts or 950 millivolts, who cares that within noise margin whatever happens, let it happen. Okay, I damn care. And it only carries at a time only 1 bit of information, 1 or 0. Compare it with linear analog circuits, it's highly linear, extremely sensitive to noise. Okay, you can just see if that signal has some more noise, it will transform immediately at the output. Any variation in power supply means bias point will vary, means one side may become non-linear, one side may become linear. So very sensitive to power supply value. Okay. And carries n bits of information, in the sense it's analog, so it's an n bit of information is going in one go. Okay. That's why it's very good essentially. Okay. One more figure will come. Here is the advantage of digital. You can see it's not very clearly visible, but maybe I'll read from here. This is an input I have put, and this center line is threshold. So anything above is 1, anything below. You can see there is a small variation is occurring below, okay, but it doesn't matter to me. It's less than threshold, na? Still recognized as 0. But if that happens in this, now you can see from here, this will be visible to you. As soon as it goes, it also jumps. Okay. So anything in digital is acceptable, whereas in analog, it's not acceptable. Okay. So this is your VDD variation. So you can see VDD variation will also appear at the signal outputs. You can see this is my VDD variation. This is overreading that, because that will change the bias point. So it will also show you the different gains, different outputs. So worry in analog is so-called noise overreading every time if you don't take enough care. In digital, I damn care. Okay, irradiation some other day. I don't know whether it's visible to you. Okay, maybe just tell you. There are 3 ways amplifier, generic will show you this latter. 3 possible way of mass realization of amplifiers. Okay, so what we have to consider in analog is handling of positive and negative signals. In digital, we are only 0 to 1. Is that correct? 0 volt to 1 volt, 2 volt, 5 volt, whatever supply. In analog, minus भी है और plus भी है. तो dual rail है, minus VDD plus VDD. So 2 power supply जा रहे हैं. Okay. Signal minus में भी आता है, plus में भी आता है. Sinusoid है, square है. So you need dual rail disc. I just now told you in the figure, where do I bias is very important, because that will decide my noise. I mean noise immunity. Non-linearity की कहाँ आने है. So I must bias it correctly. So biasing is most important aspect in analog design, because that may decide my all of the power delivered to the outputs. Linearity is essential, because otherwise what I was avoiding, I will immediately get you. I will lose power in harmonics. So I need linearity. I want noise tolerance. Sorry, the word is slightly made a mistake. I want lower noise, not tolerance. It essentially means it can tolerate larger noise. I mean, it should tolerate larger noise, but doesn't happen. So it will have a very low noise tolerance in normal system. Therefore, you must design for it that it at least tolerate this much noise. Nothing should drift too much. Power supply should not be 1 volt and suddenly 0.8 volt. Everything will haywire. Okay. It's called drifts. The problem with design is, in case of digital, as I said, we can have pre-designed, pre-tested blocks. I have a multiplier, I have a multiplexer, I have an adder. I can once design for a given technology, store it, and whenever in a larger circuit, I'll just replicate that. Nothing happens in analog that there is no standard cells. Every block you design every time. Okay. And difficulty in designing low voltage, low power, because larger the currents, larger is the charging of capacitors, as that faster. So bandwidth बढ़ाने के लिए current होना बहुत जरूरी है, power फिर बढ़ गया. So that is our major worry, to make it low power. Four important parameters we have been looked into designs. One is called transconductance. What is transconductance by definition? Transconductance, GM, output current divided by input voltage, or change in output current to the change in input voltage, delta I by delta V is GM. So one of the major parameter of design of analog circuit is the GM. Kitna GM? And you will see later GM is proportional to I, root I or some I current. So if you want a gain which is GM into R, you need larger GM. So what does that mean? Larger GM will come from where? Larger currents, larger powers. So gain at the cost of power, no other way. We'll see alternate way then. We also want to control output resistance. Some systems need very low output resistance. Some systems connection needs very large output resistance. Can we vary output resistance of a system? The third parameter of interest to me is called noise, which is called input referred noise. Now this is a very interesting word. Why it is not called output referred noise? There must be something in it. So we'll worry about input referred noise. Okay. And fourth, but it's the most important part other than the gain, is the bandwidth. Larger the bandwidth, higher frequency performance is greater, better, and therefore larger bandwidths are. We'll see a very interesting thing will happen. Gain into bandwidth normally is constant. What do I say? Gain into bandwidth is normally, quotes, is constant. Now I will see that, can we beat this word normal? Otherwise what will happen? I increase the bandwidth, I lose the gain, I increase the gain, I lose the bandwidth. Okay. So can I beat this system? I will say, I have not lost the bandwidth, but I have boosted gain. If I had done that, I have beat this so-called technological constraint. Every technology says this is the maximum gain bandwidth possible. Okay. But we will say, arey technology to technology, hum circuit hain, we will do better. Show you how do I do it, at what cost we will see. Kuch to kuch dena hi padega. I gain something. But I will see that this so-called constraint will beat. What is the constraint we said? Into bandwidth is constant, but we'll see to it, can we do mischief? Say bandwidth. Opposite is not possible. Again I repeat, bandwidth increasing and gain constant is not very easy. But gain increasing without losing bandwidth is possible. Because bandwidth is related to capacitance of the transistor, that I cannot touch. Okay. So I'll say, okay, bandwidth जो कुछ है वो है, but gain तो मैं बढ़ा ही दूंगा, या कुछ gain कर सकता हूँ. Okay. Okay, maybe there is enough we talked today. We'll have some slides later. Another half an hour lecture will continue on this, and we'll show you that little more design issues, what is happening. See you then. Have a nice day. Take care.